Huh?
I asked if you were looking for anything.
Mic. Do I need a mic?
I can hear you from the desk mic. If you want to.
Okay.
A lavalier mic, I can bring it for you.
Oh no, that's fine. If you can hear that. All right, let me put something up. Yeah, you know, I was going to comment to the students here in the. There's only a couple of students. You know why? Homework. I bet you anything. The rest of them are trying to do their homework. Okay, well, so last time, let's see. Oh, wait a minute. Yeah, now tonight the homework is due, and tonight I will finish all the material that we will cover for the midterm. Again, the midterm is next week. It's next Wednesday night. I think it's 6:30. I think it starts, and I'll talk about a little bit more toward the end of the lecture. Also, I will send out some sample problems to help you study, prepare for it, in addition to the solutions to homework 2. Now, as I said last time, with homework 2, I want to post the solutions this weekend, like Saturday, first thing. So if you need an extra day or two, 2 days is about it. So try to get it in. Okay, well, I guess I'll go ahead and get started, kind of where we left off last time. So last time we started talking about digital filter examples. We have several to go through, so I try to go through the rest of them tonight. And as I said, there was a set of notes, EE483 added notes, digital filter _4. So that's kind of what I'm going through right at this point. Now there's one thing I did want to point out. I encourage all students who are doing the Matlab problems, if you're not doing so, I encourage you to use the, or at least try out the filter function, the Matlab filter function. Now, I know that Matlab has a lot of other functions, like the convolution function, which you could also use. But the filter function is very handy. I don't know, can you, oh, you can see that, I guess. Maybe you could zoom in a little bit more closely on that. The way Matlab is structured for the filter function is if you look at the difference equation for a filter, for a digital filter of this form, and you see it as coefficients in front of the y, these are the feedback, the so-called feedback coefficients, A0, A1, all the way up to A sub n. And also you see a set of coefficients in front of the input. Those are the so-called feed-forward coefficients, B0, B1, etc. So what happens is, when you take a Z transform, you end up with this form. Can you, excuse me, can you zoom in a little bit? I don't know why, but I can't hardly see this. But you can see it. You can see it okay. Zoom in a little bit more. A little bit more. Zoom out. No, I don't know. Can you?
Oh, yeah, zoom out.
Oh, no. Oh, geez. No, zoom in. The other way. Okay, yeah, good. Well, see on my monitor, this thing doesn't zoom in as much. But anyway, what I was saying... Oh yeah, so that if you take the Z transform of this difference equation, as we discussed last time, you end up with this form for h of z. And once again, you see these coefficients, B0, B1, in the numerator, A0, A1. The way the Matlab filter function works, so once again, it's very simple once you get used to it. Now, pardon me. Now, I've talked to a couple of students who have used like convolution. That's fine, but if you want to use the filter function, like I said, once you get used to it, it's pretty simple. So if you have a difference equation, of the form, so Matlab filter function. So to use it, if you have a difference equation of the form a naught times y of n plus dot 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 plus a sub, I don't know, a sub n y of n minus n equals b naught. So if you can get your filter difference equation into this general form, plus b sub m times x of n minus m, then to use the filter function for any input sequence x, you define the a vector like so, a naught, a1, or you know what, in Matlab you can either use commas to separate the entries, spaces, or you can use semicolons if you want to make a vertical array. So a, well, etc., all the way up to a sub n, and the same thing for b, see? Now where it gets a little confusing, b sub m, and at that point, once you've defined your array, say you want to find out what the impulse response of this, then you could define an array, or a step response, like in problem 8 in this homework, on the Matlab exercise. I asked you to determine the step response, but let's say you wanted the unit impulse response. Then what you would do is you first of all define x, and the way I do it, again, is zeros of 1 comma, well, I've already used n and m, let's use L, and then x of 1 is equal to 1, and then you just do y equals filter, and that's it, b, comma, a, comma, x, and that will automatically produce for you the filter response in the output vector y. So it's useful to get used to it. Now the only well, I wouldn't call it a trick, but a lot of times we've written, for example, we've written filter functions in the form y of n is equal to a times y of n minus 1 plus b. Now the only thing to keep in mind is that the way the Matlab filter function works is that it assumes the coefficients are on this side. So if you have a so if you write it like this, see, then you have to put that back to this side minus a times y of n minus 1. Oh, I'm sorry, that should be x of n. Is equal to b times x of n. That's your difference equation. So in this case, well, let's say, let's see, let me call that a naught. Call that b naught. Where b naught and a naught is just a constant. So then you would have a, so I don't confuse it with the vector. A would be the vector, in this case, 1 minus a naught. So that's the only thing that, and the b vector is just one element, namely b naught. And then you're off and running. So the only thing that confuses people sometimes is they see the difference equation written in this form, and they forget to transpose the terms over to the other side. But in any case, just a note, it's a very useful function, and it's very nice, because the thing is, the convolution function, well, no, the convolution function would work. That's fine. The convolution function would work if you can define the impulse response and the input data vector. You do CONV of h comma x. That'll work too, but this is pretty useful. So just a note, you can give it a try. Anyway, so we talked about that last time, and what else? Oh, we went through some examples of where I had specified the poles and zeros and asked you for the z transform of the difference equation, and ultimately for the linear difference equation itself. which was of this form. So again, I make a note to yourself. This is relevant when you start doing the first class project. And then we talked about some cascaded systems and impulse response. And the message there for the cascaded systems is the simplest way to analyze a cascaded system, or really any system, is through the Z-transform. If I give you time domain expression for the impulse response, or in this case the input-output, always convert it to the Z-domain, where everything becomes much easier. So that is kind of some examples we went through. Then we start talking about specific examples of digital filters. We talked about the simple averaging filter, like basically the filter takes a running average, and then we defined it in DSP terms, we characterized it in terms of an actual impulse response, which turned out to be finite, and assuming that we're averaging over a finite number of samples, obviously a running average, we can characterize that in terms of a digital filter with a finite impulse response, hence the term finite impulse response system, or filter, FIR filter, and we derived its Z-transform and discussed its pole zero plots, and even discussed the frequency response of this system. And I think I went through a couple of different ways of implementing this filter. So we covered that last time. We kind of ended on the recursive smoother. The recursive smoother is, oh wait a minute, let me forget. Let me get that here. Yes. The recursive smoother is a very simple filter, and it is in the form I was just showing you as an example using the filter function, namely y equal of n equal a times y of n minus 1 plus x of n. That's the recursive smoother. You can analyze that with the filter function. You should know how to do that now. But in any case, and we'd already talked about that when we had much earlier when we talked about geometric sequences, right-sided geometric sequences, because the impulse response is a right-sided geometric sequence, as we've shown many times in the past, and its frequency response kind of changes shapes depending on the sign of this constant a. If a is positive and less than 1, then the frequency response looks like this. I sketched it for two hypothetical values of a. This value of a here, and this value of a, which is closer to 1. So you get kind of a bigger response near omega equals 0. Hence, this is would be considered a low-pass filter. Of course, as a goes to 0, then it's really just a flat filter response, obviously, because y is equal to x in that case. If a is negative, as we discussed, then the filter response really does change shapes, and the peak now occurs at omega equal pi. So this is more like a high-pass filter. So the beauty of this, of course, is versus the running average filter, is you can change the frequency response just by modifying the value of this one constant as opposed to making a longer filter. So we talked about that last time, and now we're ready to talk about another filter which will be of interest to you in the first class project, namely a notch filter. The first class project you will consider actually a real version of this, but this will kind of give you insight to what a notch filter does. So we start off with the notch filter. It's of the form y of n minus a times y. This is first order now, equal x of n minus b times x of n. Oops, I ran out of room. B times x of n minus 1, rather. Okay, that's the form of this first order notch filter, where a and b are complex and they're related to each other. Okay, So that's what I call a first-order complex notch filter. So what are A and B, and what does it look like? Okay, so actually the constant A, if you look at this example, is equal, can be written as A, A e to the j omega naught, where A is real, little a is real, I should say, in between 0 and 1. Less than 1. And B is just equal to e to the j omega naught, okay? And again, omega naught is between generally pi and minus pi. It goes all the way around the circle, okay? So that is a complex first-order notch filter. So let's see why we call it a notch filter, and let's kind of figure out a little bit more information on it. Well, first of all, so this is my difference equation, and it's just exactly what I said, y of n minus a e to the j omega naught times y of n minus 1. So that's that term and that term. You notice that b, b is of the form e to the j omega naught, so the complex magnitude of b is 1. Okay, in other words, this point, e to the j omega naught, is right on the unit circle. Okay, this a value is a e to the j omega naught. Its magnitude, complex magnitude, is little a. And since little a is between 0 and 1, it's a little bit off the unit circle, depending on the value of little a. So let's see what the Z transform of this filter looks like. And here it is. And the first thing you want to look at when you get a filter like this is, well, there are a lot of things to look at, the frequency of response and so on, but one thing you want to look at is you want to look at its, another thing too, I should say, this is causal, okay? So causal is a code word. What do they call it in a dog whistle? for all of you DSPers, causal is a dog whistle for meaning that it's a right-sided sequence or a right-sided system. Okay, so that means the impulse response right-sided. It vanishes for n less than some sample, and in case and when it's causal, that means it vanishes for n less than 0. As we know, this causal system is for a linear time invariant system is causal if its impulse response vanishes for n less than 0. So causal right-sided impulse response, same thing. So here is the Z transform. So you should make sure you know how to do this. This is a useful example to kind of go through and see what I'm doing, because it does relate to the first class project, and it gives you a little more practice in doing these transforms. So anyway, transform the right-hand side, you get this numerator. Transform the left, you end up with the denominator. And so it looks like that. Now in this case, if I were to use the filter function as an aside, then the coefficient vector for the feedback would be 1 comma minus a e to the j omega naught. That's right, it would be complex, but there's no problem using complex with the Matlab filter function. So anyway, it looks like this: 1 minus e to the j omega naught z inverse over 1 minus a e to the j omega naught z inverse. So the first thing you'd want to, well, ultimately you want to know what is the region of convergence of this. But since we used this causal code word or dog whistle, we know that the region of convergence is going to be exterior to some circle. The radius of the circle will be defined by the pole or poles of the system function, or Z transform of the impulse response. Now in this case there is one pole, and the pole occurs at a e to the j omega naught. So that's the guy that's kind of slightly inside the unit circle. There's 1 0 at e to the j omega naught, which occurs on the unit circle. So if you were to draw the pole 0 diagram, this is what it would look like. X, see that? The X inside the unit circle, and the big O for the 0, that's on the unit circle. And what would be the region of convergence of this Z transform? Well, it would be, if you draw kind of a dash line here, this is of radius A, it would be basically everything exterior to that, see? So that would be the ROC. So the ROC is the set of all z such that the absolute, not somebody had worked on one of the homework sets, well, here, let me show this, greater than little a. Somebody done where I had a complex pole, and they said, oh, the ROC, isn't the ROC in this case z greater than a e to the j omega naught, question mark, and the answer is no. No, absolutely no. This is not a region of convergence. So its magnitude, complex magnitude of z is greater than a, which implies that it is everything exterior to a circle with radius little a. So the next question you ask, okay, I want just checking, is the filter stable? Well, yes it is. Yes, Cerritos. It is stable. Why? Stable, question mark, and the answer, big yes. And it's stable because the region of convergence includes, or I should say the other way, the unit circle lies within the region of convergence. Because that's the unit circle is also exterior to the circle with that radius little a, because a is less than 1. So anyway, like I said, you can tell a lot about the system just by looking at its pole zero diagram, but you can also tell a lot. As I said, you analyze, you can get properties of the system by looking in the transform domain, z or frequency, and yet you implement by actually going back to the time domain representation. So what else can we tell about this system? Well, if you sketch out the frequency response, remember the frequency response is obtained by taking a point on the unit circle and just running it all the way from 0 to 2 pi, or pi to minus pi, either way. But you just go all the way around this circle, and as you go around the circle, you evaluate h of z, or h of e to the j omega, take the magnitude. So look, as we start off walking around this circle, what are we going to run up against? We're going to hit this guy, see? So we know right there that if we have a 0 on the unit circle, that the frequency response has to go to 0 at that frequency. So here is some sketches. Now, as a approaches 1, it's almost like the pole right here almost cancels the 0. But as a approaches 1, but still slightly less than 1, here's what's going to happen. As you get this pole right next to the unit circle, it's almost like the pole and 0 are going to cancel. You get 1. You won't get 1 because as long as the pole is less than 1, in other words, it's inside this unit circle, you're still going to get the 0 at omega naught. But what's going to happen as a approaches 1 is out away from that omega naught. Things are going to look very, very flat, see? But you know that as long as a is less than 1, strictly less than 1, right when omega equals omega naught, bingo, you're going to get a 0, okay? So the point of fact is you can build very, very sharp notches, something that would be practically, I mean not impossible, but would be very impractical with a very long FIR filter. With this little simple filter, you can build very, very sharp notches simply by increasing a closer to 1. Okay, bingo, like that. As a becomes smaller, closer to 0, you will still notch things out at omega naught equals 0. But what will happen is your notch is no longer very sharp, so you'll start knocking out components quite a ways away from this notch frequency omega naught. So, for instance, so what? Well, here's so what. So suppose your input, suppose I were to generate for you an input with a dTft versus omega that looks like this. I'll make this omega naught. And it will look something like this. I don't know, I mean, just something kind of flat. Here's pi. But right at omega naught, there's some interference. very strong interference. This is interference, okay? So your signal looks like this, but then there's a strong interfere. Well, obviously what you want to do, read this first class project, is that you want to get rid of this, but you don't want to mess this guy up. You don't want to mess the signal up. As you let the notch, as you let A get closer and closer to 0, you will start to see a very, very wide notch, a very sloppy notch you can think of. So for this case, A much, much less than 1, you will distort a signal. Let's call it a wide band signal. There will be a lot of signal distortion. Okay? Whereas if the interferer is just like a sine wave right at this frequency, then what you really want to do is build a very, very narrow notch, a very sharp notch. So you would ideally want A to approach 1 for this case. So anyway, in the first class project, you will get a chance to play around with these notches, and you can see what you would get. So that is the story of this very simple notch filter. Now, in the first class project, actually what you end up with is a real notch. It's sort of the same thing. Where is it? It's sort of the same thing as the complex notch, except that, and I've scribbled over this, it actually has complex conjugate poles and zeros, okay? And that turns out to make the system real, because I wanted to do a project where we had to use a notch filter with a with a real input. I wanted to build a notch filter. So what the real notch filter, it has a pair of poles and zeros, at plus omega naught and minus omega naught. But still, if you plot the frequency response out, as this pole goes close to the unit circle, once again you will see a sharp notch. It'll just be at plus and minus omega naught, which is what you would expect with a real filter. Remember, when you have a real signal and take the DTFT and plot the magnitude, it's symmetric, about omega equals 0. So that's all. But it's the same idea. This is the same idea as the complex. So look at the complex notch. It'll give you a little more insight into what's going on. Now, one final comment about the complex, or about this notch filter. As I said, the sharper it is, the less signal distortion you're going to get, the closer A is to 1. And if your interference is a very narrowband or sine wave interference, and you know the frequency omega naught, perfect, build a sharp notch. Now, if you don't know the frequency, that's why, well, I don't quite know that frequency omega naught, so I'll build a little bit less sharp notch. So I'll make sure if the interferer is a little bit off, I'll nail it. And that's true, you will, but you can't get something for nothing. You will introduce more signal distortion. Okay, so this is like, I don't know, 50%, 70% of the story. There's another part to this story, and this is all frequency domain. Now let's take the frequency domain and go back to the time domain and see what the impulse response of this thing looks like. So if you look at the second page of this, as I said here, pardon me for this thing. So now suppose that we programmed up this difference equation. See? Suppose we took that and programmed it. And we could program it with the filter function. The Matlab filter function will work fine. So you'll make the A vector. Oh, let me just do it like this. You can generate Y equal filter. In this case, it will be 1 minus e to the j omega naught, comma, 1 minus a e to the j omega naught, comma, x. That would be a way of generating the filter response. I guess that didn't come out too well. But in any case, this is the A vector for the feedback coefficients. It's just I'm sorry, this is the B vector for the feed-forward coefficients. And there's just two the one coefficient's 1, and then minus e to the j omega naught, and that component is complex, and then there's a vector for the feedback, and they both have dimension 2 for this case. In any case, when you went to program that, and you with x of n equal e to the j omega naught n. Okay, so we're going to say we have all I'm going to do is input a sine wave right at that notch frequency. But wait a minute, I can't generate a sine wave that goes on forever. I have to start it at some point, so I will start it at 0. So this will be my input. Now the question is, so what do you think the output will be? What will the output be for this case? Y of n. Will it equal 0? For n equals 0, 1, 2, 3, 4. What does it equal? What does y of n equal? Well, it turns out, thanks to the notes on the z transforms that we covered, it turns out that you can calculate exactly, not even without using the Matlab filter function, using inverse z transform. It's very simple. You can actually analyze this directly. Now, we know that y of z, and I'll just write this out, but I've written it also, it's printed here, so, is equal to h times x. We know that h is equal to 1 minus e to the j omega naught z inverse divided by 1 minus a e to the j omega naught z inverse. So we know that. But what about x? What is x? E to the j, what does that equal? Or, I'm sorry, x of z, what does that equal? Well, we know that x of n is equal to e to the j omega naught n times u of n. Let me write this in a slightly different form. Let me write this as c to the n. This looks like a geometric sequence times u of n, where c is defined as e to the j omega naught. Granted, same thing. C to the n u of n, where c is e to the j omega. That's x of n in this case. Okay. Well, now c to the n times u of n. That's a right-sided geometric sequence. That right there automatically implies that x of z has got to be 1 over 1 minus c, where with region which is equal to 1 over 1 minus e to the j omega naught, with ROC absolute value of z greater than 1. See that? Voila, done. So now, what is y of z? Y of z is equal to, well, oh, I'm sorry. Sorry. A little carried away. Forgot the z inverse. So what y of z is, well, check it out. You see that 1 over 1 minus e to the j omega naught z inverse? What's that going to do? Pole zero cancellation. So this pole of x is going to cancel out the 0 in h, and you're going to be left with this. 1 minus a e to the j omega naught z inverse. Okay? Again, with ROC, since everything is causal, including the output, z greater than absolute value of a. Well, we assume a is positive, so that's just a. So that's y of z. So now my next question is, what is y of n? Well, if you look at it, this is actually of the same form as this, so it has, it's running out of space, y of n must equal to c, let's call it d to the n times u of n, where d is now a e to the j omega naught, so this is equal to, defined to be a to the n times e to the j omega naught n times u of n. So it's basically a right-sided geometric sequence. It does go to 0. If you were to plot the magnitude of y of n versus n, you would find that it would go right to 0. Okay? But it doesn't go immediately to 0. So to answer your question, even though I put a frequency right at the notch frequency, does it notch it out for all time? The answer is no, it doesn't. It takes a while. It will notch it out. Ultimately, it'll get rid of it. The filter will get rid of that sine wave that it'll make it up, but it takes time. See? Now, the next question is, how long does it take? Well, it all depends. This is going to take longer as a goes to 1. See? As a approaches 1, you remember that point where we got the sharper notch? Yeah. Well, that's great in the frequency domain. The notch is sharp. But in the time domain, it's going to take longer and longer to settle out. The filter will have this transient response, and it'll take much, much longer as a approaches 1. So for the sharp notch, so basically, well, here. Thus the filter out, I'll go back to my notes actually. Thus the filter output is this, which decays to 0 as n goes to infinity. The moral, this is the difference between time and frequency domain. Sharper notch implies, that's a approximately 1, implies longer settling time or response time, longer response time. So it's just something to keep in mind. If you're trying to use one of these filters to notch something out, you have to wait long enough for all the transients to decay, because initially this will not be 0, and it won't be 0 until this thing has converged. It'll never, y of n never actually goes to 0, but it approaches 0 very closely. So that is the story of this first order notch. And if it's a second order real notch filter, like in your project, you can do the same trick, except you will have 2 poles and 2 zeros, so you need to do some kind of partial fraction expansion. But you can do the same type of analysis, and that's what you will find.
Professor?
Yes.
So y of n a sine, sort of like a sine wave?
Yes.
The same sine wave?
Yes, yeah. If I were to draw, like, let's suppose I plot the real part of y of n, kind of hard to draw the complex version. Yeah, then that would be a to the n times cosine omega naught n. So that actually would do stuff like this, you know. It would decay, but the decay would be exponential. But yes, you're right. So that's, and that's actually what you would see. But in any event, that is an important moral in terms of frequency versus time. Sharper in frequency, not as sharp in time, and vice versa. So that is that. Here's another example of a filter. We don't really have much need of this, or I should say we won't really use this in our projects or anything, but I'll mention it to you. Hang on, just bear with me. Yes. I will mention it as we pass along. I won't go through all these examples, but some I tried to. This is a second order unity gain resonator filter. Basically, it is a bandpass filter, okay? So we talked about low pass, high pass, notch. This is called a bandpass filter. And it has a very simple form for the difference equation and a relatively simple form for h of z. For this one, h of z, but now, like our real notch filter, it is really quadratic in the numerator and the denominator. This looks like 1 plus a1z, the minus 1 plus a2 times z to the minus 2. Oh, I don't know what that was. Anyway, 1 minus z to the minus 2 over 1. I wrote it down here. I'm just writing out so I can read it. So now this has poles and 0. It has multiple zeros. It has zeros at, as I mentioned here, plus or minus 1. And it has poles. We assume that the A1, A2, all of these are real, see? Real constants, real coefficients. Which means that if we were to apply the quadratic formula, you would find that the poles occur in complex conjugate pairs. So I went through and wrote what the pole representation would be, and it turns out, if you sketch, and I won't spend much time on this particular filter example since we don't use it, but if you plot out the poles in zeros, you will find that you have you have two zeros at pi, or at 0 and pi, and then you have two poles here, of course, off the unit circle, and if you draw the circle enclosing that, you will find that, as usual, it's a stable filter. And these poles occur on radials at angle omega naught. Now, it turns out if you draw its frequency response, as it turns out, I have a couple of notes on drawing frequency responses, so I'll wait till I get to that. But as it turns out, the maximum, now before in the notch filter, the 0 occurred right at the notch frequency. That's because our zeros were right at the notches, see? But here the zeros are off at plus or minus 1. So it turns out as you walk along the unit circle, you get close to omega naught, you'll actually have a maximum. Depending on where this pole is, you'll actually have a maximum because that's closest to the pole. So it turns out that if you choose the constants appropriately, as I define in the set of notes, you will find that if you sketch the magnitude frequency response, you will indeed get a peak right at the particular frequencies that you chose. And so with a maximum magnitude of unity. So that's why these are called what's going on? Oh, I see. What? Oh, yeah. Sorry, I got confused. Yeah, that's why these are called second-order unity gain resonators. They're basically bandpass filters with max values of 1. So what they do is, if you have an input which has, some energy across frequency here, what it will do, it will accentuate or enhance any signal components at this particular frequency. So if your input signal, so these are ideal for, suppose your magnitude of my input versus frequency had some signal of interest right at omega naught. Okay, this was not interference in this case. This is a desired signal, but then out here there's a lot of noise. So this is the desired signal. Then you would want one of these unity, or you could also build a FIR filter, but you'd probably want to consider one of these resonator filters, because you can design the filters depending on your coefficients to attenuate or to accentuate any of these frequencies with maximum gain of 1. And again, like I said, in the notes I define all these constants, but since we're not going to use it, I will move on. The next set of filters that I want to spend any time with on all of these examples are what is called the all-pass filters. Now these are very interesting. All-pass filters are filters whose magnitude of the frequency response across all frequencies is equal to 1. No matter what the frequency is, the magnitude is equal to 1. So what would be an all-pass filter? Well, people that see this say, well, this is not interesting. Look, this is an all-pass filter, x of n, h of e to the j omega naught of omega is equal to 1. And the same thing with y of n, So these are examples. 1, 2, y of n equal x of n minus n naught, and so on. So you're thinking, or you may think, again, h of e to the j omega, magnitude in this case, is equal to 1. Okay? So you're thinking, well, all these all-pass filters do is either just copy the signal or they delay it, and that's it. So what's the interest in these? Well, that's only a small part of the story. It turns out all-pass filters are a lot more interesting than this, and they can be constructed with non-trivial, what I will call non-trivial examples of all-pass filters with arbitrary phase responses. See, so an all-pass filter has a response, frequency response, looks like e to the j phi of omega. See? That would be an all-pass filter. So all I've said is the magnitude is equal to 1. I didn't say anything about the phase response. And it turns out these all-pass filters can be designed to have an arbitrary phase response. And one classic way they're used, or reason they're developed, is this one I've sketched out here. Suppose you want to do a high-fidelity bandpass filter, which has a huge dynamic range on the filter. So you really want to get rid of everything outside of the signal that you want to accentuate. You want to get rid of it by 100 dB or some large number. Well, the way to do that turns out is to use what we call the infinite impulse response filter. This could be an IIR. And what is an infinite impulse response? It's just what we've been talking about. It's filters with poles and zeros, or zeros and poles, I should say, as opposed to a finite impulse response filter, which only has zeros in its C transform. So, suppose you built a very high fidelity bandpass filter, okay? So you feed x of n into this. The problem is, even though you can design the amplitude response, you can't necessarily design the phase response. In fact, the phase response can be horrible of this high fidelity bandpass filter. In which case, if you take that output, yeah, it will get rid of these unwanted frequency components, but it will distort, phase distortion of your signal. And if you have a audio system, high fidelity audio system, now a lot of systems have this built in now, then that can be a real problem, see? All that phase distortion will screw up the signal. So what people do is they say, aha, well, tell you what, I will build what is called a phase equalizer. And what the phase equalizer does, see, I like the amplitude response, the magnitude frequency response, I like that. I just don't like the phase response. So what people will do is build a phase equalizer. It doesn't do anything to the amplitude, it just equalizes or undoes the phase distortion. What would be a perfect filter to do that? All-pass. That's exactly where the all-pass filter is used. And like I said, I give you some simple examples of all-pass. Let's take a more interesting example of all-pass filter where we can actually design it to do this phase equalization. And here is the, I don't know if you can see this, but this is the general representation of an all-pass filter with non-trivial coefficients, and in this case all the coefficients are all the coefficients are real. You can also have one, if you want, with complex coefficients. All right? Now, you notice what I did? Very interesting. There are n plus 1 coefficients, and that's it. Now, you might say, well, there's n plus 1 here, there's n. No, wait. These coefficients are actually the same as these coefficients. It's just that kind of in reversed order. You notice that? So here, a naught z to the minus n, a1 z to the minus n minus 1, dot, 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 all the way to a sub n, which has no z inverse in front of it. The denominator, on the other hand, is just the opposite. A naught is the leading term with no z inverse in front of it, and you go all the way down to a sub n z to the minus n. This is an all-pass filter. If you compute the magnitude frequency response of this filter, I guarantee you it will be 1. And how do we see that? See? How do we see that? So that's what it looks like. So here's how we can see it. As it turns out, h of z, if you play around with the numerator, so the numerator, n of z, looks like a naught z to the minus n plus dot, 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 and it gets all the way to a sub n. Now, do this. Let's factor out a z to the minus n. Check that out. Then what do you get? Well, you get a naught plus dot, 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 and then you will get a sub n
C to the n.
yeah, a sub n. Oh, I guess that's right. Z to the n. Yes, yeah, that is right. Okay? Now, that looks almost like, let's review again our denominator. Our denominator is a naught plus dot, 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 plus a sub n z to the minus n. See? So this looks pretty close to our denominator except for one little thing. And in fact, if you look at, oh, well, okay, let me look at it this way. Now, let me take z to the n, and I will factor this, I'm sorry, d of z, and factor out this. What do I get? I get a naught z to the n plus dot, 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 plus a sub n. You see? So it turns out, and this looks exactly like no, that isn't right. Oops. Okay, this is d of z. All right, scratch that. Let's do this. Let's take d of z inverse. Aha. And what is that? That's equal to a naught, sorry about this, plus a sub n z to the n. Okay, that's d of z inverse. Now let's look at z to the minus n times d of z inverse. That's what I wanted. That's equal to a naught z to the minus n plus dot, 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 plus a sub n. And that is equal to the numerator, n of z. That's what I meant to do. Okay? And I've written it down here. I was just trying to go through it, and I got messed up. But anyway, so the denominator and numerator polynomials are related through this. Just what I've written. Z to the minus n, d of z, the minus 1. Okay? So that's how those two are related. Now, let's look at the magnitude of h of e to the j omega. What does that look like? That looks like the magnitude of e to the minus j omega n. So in other words, I just substitute z equal e to the j omega times d of e to the minus j omega magnitude divided by the magnitude of d of e to the j omega. Okay, you see that? And again, I'm just repeating what I've written down here. But guess what? Look at the numerator. This is the magnitude e to the minus j omega n times d of e to the minus j omega. Well, one thing you can do is you can get rid of the magnitude of e to the minus j omega n is 1, so you can write this as d, the magnitude of d of e to the minus j omega, divided by the magnitude of d of e to the j omega. Now, what is that equal to? Well, don't forget, this numerator, I'm sorry, the denominator, see this, a sub k? They're all real coefficients. And we know, if we have a real coefficients, we know that, but a sub k are real. So what that implies is there's complex conjugate symmetry. D of e to the j omega is equal to d of e to the minus j omega, complex conjugate. Okay? Complex conjugate symmetry. So this is a very good example to go through because there's several things happening. You sure get practice using your complex arithmetic. And we furthermore know, don't we, that the magnitude of, I don't know, call it C, where C is complex, is equal to the magnitude of C complex conjugate, right? Right? So what that implies is that the magnitude of H is equal to the magnitude of D complex conjugate e to the j omega divided by magnitude of d of e to the j omega, which is equal to 1. Okay? So it just, and again, I just repeated everything I wrote up there, but I tried to go through it to give you more of the steps. So what it says is that if we construct a filter with coefficients in the numerator and denominator, just in backward order, okay, reversed order from the numerator to the denominator, if we construct a filter like that, we have n plus 1 degrees of freedom. We're guaranteed it's an all-pass filter, and with those n plus 1 degrees of freedom, we can modify the phase, equalize the phase, and that's how these phase equalization filters can work with all-pass filters. So that's a very interesting property of these so-called all-pass filters. And as a final note, if you look at the pole zero diagram, you will find that the poles and zeros are along the same radial lines, okay? But in this case, the zeros are outside of the unit circle. But somebody asked me once, well, does it matter if the zeros are outside of the unit circle? No, it doesn't. That's fine, because the poles are inside. It's a causal filter. So once again, I draw this. Here is my circle, and here is my ROC. The fact that zeros lie in my ROC, I don't care about. Just as long as the unit circle lies in the ROC, so therefore it implies it is stable. Okay? And zeros do lie in the region of convergence. No problem. Okay? So that is the story of the all-pass. So again, I encourage you to review. Yes, sir.
I have one question. So you talked about the magnitude of H.
Yes.
Can we go over what happens to the phase of H?
Oh, well, yeah, yeah, the phase, the phase is a little bit complicated. I mean, the way you would do it is the phase, trying to see, the phase would be equal to, or here, let me draw it on here. So we know that h of e to the j omega, you can think of it as e, what did I say, e to the minus j omega n times d of e to the minus j omega minus, right, divided by d of e to the j omega. Now, one thing you know about the phase is that, so this is, I can write this as, I don't know, I want to write it in a simple term. I'll just say k divided by q, I don't know. Where k and q are defined, so I'll write that as triple, equal, defined to be. So I know that the phase of h, and I furthermore know that I can write this as some magnitude, which is 1, right, times e to the j phi sub k divided by e to the j phi sub q. Now, again, you know that k and q, k will turn out to be this, q will turn out to be this, so I can write this as e to the j phi sub k minus phi sub q. So the phase is just equal to the difference of the phases of these polynomials. So what is that going to equal to? Well, first of all, don't forget this. You'll have this phase, so that's going to be, and that'll add to this phase. So this will be a minus omega n plus the phase of d of e to the minus j omega, and that'll be minus the phase of d of e to the j omega. Okay? Now, the other thing we know is that since d is real, or the coefficients are real, we know that d of e to the minus j omega is equal to d of e to the plus j omega complex conjugate. So what that implies is that the phase, and we talked about this last time, or not last time, but a while ago, we talked about dtft's of e to the minus j omega is going to turn out to be minus the phase of d of e to the j omega. Now what I'm doing is I'm taking as far as I can go, so I'm almost there actually. So finally that implies, and this is as far as I can reduce it, that the phase of the all-pass filter can be written as minus omega n minus twice the phase of d of e to the j omega. Now, again, the d, this term here has, is written as an nth order polynomial in e to the j omega. So the way these phase equalizer programs work, they're nonlinear. What they do is they attempt to make the phase minus the phase of this bandpass filter to be as small as possible using least squares technique. So they can vary the coefficients to change the phase response here, and they try to change that in a way that it minimizes the phase distortion here between this bandpass filter. So anyway, that's good exercise. Thank you. I feel like I've run about 1,000 miles. Okay, again, all this you didn't copy it out. Don't worry, it's all going to be scanned. And you'll have the notes, so I encourage you to review the notes. Before our break, let me talk about another example, and this also will be highly relevant to you as you're doing your first class project. So I tried to put in, basically emphasize these notes by putting problems similar to this in the projects and the homework. So it kind of gives you a motivation for studying these notes. Okay, this is something called a comb filter. As you can see, it doesn't work on me too well, but it might help you. It will help you in your project. These are used for a lot of things, but one thing they can be used for if you have an interferer at a frequency omega naught, and then you have another interferer at frequency 2 omega naught, then 3 omega naught, then 4, and there's harmonic. We call those harmonic interferers. One notch filter may not get rid of all, in fact it wouldn't get rid of all those, but a comb filter could. So comb filters are very important, and again you will have an opportunity to have some practice with comb filters in your first class project. So what is a comb filter? Well, generally you start with, and I will call this a prototype filter. Prototype filter. And I will call that H of Z. Now H of Z could be anything. I mean, it could be a low pass filter, it could be a notch filter, it could be high pass, whatever you want. And then you define, so you start out with H of Z, that's your known filter. Then you define H sub k of Z. You define that to be H of Z. So you define it in terms of this prototype filter, okay? Or in the frequency domain, H sub k of its frequency response can be related to the frequency response of the prototype like this, e to the j omega k. So I took, and I'll explain this a little bit more in just a moment. So that is what a prototype filter is. Here's an important example. Oh, but first, let me just in words say this, and I'll go back to some more notes on this. Since h of e to the j, what do we know about h of e to the j omega? Okay, what about h of e to the j omega? Is what? Is periodic with omega equal 2 pi, or multiples. In other words, h of e to the j omega plus 2 pi is the same as h of e to the j omega. So, h of e to the j omega is periodic in 2 pi. Well, then, what does that mean? That means that h of e to the j k times omega plus 2 pi over k is going to equal to h of e to the j k omega. So in other words, what that means is that h sub k is of course it's periodic in 2 pi, but more importantly, it's periodic every time omega increments by 2 pi over k, you get the same result. So if h of e to the j omega is periodic in 2 pi, then h sub k of e to the j omega, which is h of e to the j k omega, it's got to be periodic in 2 pi over k. Thus, h sub k has a periodic frequency response. This type of filter is termed a comb filter and is very useful in filtering out noise from signals which are rich in harmonic content. Actually, in filtering out noise, the noise has to be rich in harmonic content. Alternatively, or suppressing power line harmonics, or for suppressing clutter from fixed objects, or anything like that. Again, instead of going through a lot of examples, you'll see an example in your first class project. So I took a very simple example here. H of z in fact, let me just no, that's all right. Let's see, comb filter example. Well, that's all right. I guess I'm doing that anyway. So here is a comb filter example. H of z equal 1 minus z inverse over 1 minus a z inverse. Now, what that is an example of our notch filter. It's just that omega naught is 0. So this is a notch filter at omega equals 0. See, it looks like this. So that is what the frequency response. So this actually could be thought of as a high-pass filter. Okay? And what is its difference equations? Right here. It's pretty simple. Y of n minus a y of n minus 1 is equal to x of n minus x of n minus 1. And if you were to plot out its frequency response, it would look like this. So it notches out things at omega equals 0. So you can think of it as a high-pass filter. Here's its pole 0 plot. Okay? So it's a special case of what we looked at before with the complex first-order notch filter. Interesting, maybe not so interesting. Aha! But let's let h sub k, what does that look like? Of z equal h of z to the k. That looks a little more interesting. And if you plot that out for k equal 8, the pole 0, so you have a pole 0 pair here for h of z, but when you look at h of z to the k, guess what? Those pole 0 pairs get replicated. This is an example with k equals 8. So now instead of replicating every 2 pi, which of course this does, now you replicate every 2 pi over 8. 2 pi over 8 is pi over 4. That's 45 degrees. So now you go 45 degrees, you get another pole 0 pair. 45 degrees more, you get another pole. You get this all the way around the unit circle. Now the filter looks a little bit more interesting just by making that one little change. If you plot the frequency response, here's our notch at 0, but then it gets another notch at pi over 4, 2 pi over 8. remember k is 8, gets another notch at pi over 2, another notch, 3 pi over another notch at pi. So if you had interference, that you had a strong component here at omega equals 0, you had another component here at pi over 4, in other words, harmonic type interference, this would wipe them all out. So this is a very, very useful notch filter. Now you may wonder, how do I implement such a filter? H of z to the k, how do I implement this? In the time domain, it has a very simple implementation. You know what you do? You go to your z domain, you look at the z transform, then you transform that back through the inverse route to the time domain. And guess what you end up with? Here it is. So actually it looks very similar to the prototype linear difference equation, except you have delays of k instead of unity delays. That's all there is to it. That will implement this comb filter. And you can do that with any filter that you want. It's a very, very useful filter, as you will find out. Now, let me say a few more words about this. Okay, again, that was with the example of k equal 8. So let me just, since it does appear in your class project, let me just repeat again. This is equal to h. So I know I'm repeating this, but that's all right. Give me a little bit more detail. Omega goes to omega plus 2 pi over k. That implies that h sub k of e to the j omega plus 2 pi over k is equal to h of e, now that's h sub k, that's equal to h of e to the j omega k, right, plus 2 pi. I just multiply. Remember this, okay, so I'm letting omega be omega plus 2 pi over k. I'm demonstrating the periodicity. I multiply that result by k, and I get this, which is equal to h of e to the j omega k. Okay, h of e to the j of 2 pi is just 1. So I get this, which is equal to h sub k of e to the j omega by definition. So that implies that that demonstrates periodic h sub k of e to the j omega, that demonstrates is periodic with period 2 pi over k. So that just, I don't know, adds a little bit more detail. And let's look at our comb filter example. Now I'm going to add a little bit more to this example by considering things, as you know I like to do, in the time domain example. And you can use this in your class project. And you should, actually, do. So here is the prototype. This is just the example I just talked about, but I'm going to fill in some more detail. Is h of z, and it's equal to 1 minus z inverse divided by 1 minus a z inverse, okay, same one we did, and we know, so I know I'm repeating, but I'll add some more here, y of n minus a y of n minus 1, is equal to x of n minus x of n minus 1. Okay, just to repeat, comb is equal to h sub k of z equals 1 minus z to the minus k over 1 minus a z to the minus k. And you have poles when a z to the minus k is equal to 1. Oops, sorry. Well, guess what? Or z to the k is equal to a. So those are where your poles are going to be located. So guess what? Okay, what that implies is that poles of h sub k of z at, there are going to be multiple poles. One pole, of course, will be one pole, so we know that one pole, at z equals the kth root of A, but there are more. There are more. And so, like this example we did with the running average filter, it turns out the poles of H, all the poles occur at z to the sub m equals a to the 1 over k times e to the 2 pi j m over k, where m is an integer and m runs between m, 0, and k minus 1. Okay? If you don't believe it, just substitute that in. Take z to the m to the kth power. You end up with a and e to the 2 pi jm, which is unity. So those are all of the roots. There are actually k roots of this comb filter. So just by adding that z to the k changed the picture quite a bit. Now, let's suppose we go a step further. This is what I didn't include before. And let's look at a partial fraction expansion without working out all the constants here. But let's look at 1 minus az to the minus k. That's equal to summation of m, a sub m, divided by what? By 1 minus z inverse, and you put the pole locations. A to the 1 over k times e to the 2 pi j m over k. See? So I've just I did a partial fraction expansion about all the poles. Okay, so I get that. What are the a sub m? Well, you have to use the techniques that we mentioned to compute the a sub m, you know, multiplying through by one of the roots and then setting that to 0, and or setting it to, setting the factor to 0, and you can end up with all the a sub m's. But that's what the final result will look like. So now let's look at implies that. Let's say we did a inverse C transform. Now we know everything is causal of 1 over 1 minus a z to the minus k. Well, if you did a z inverse Z transform of that, since everything's causal, what you're going to get is a bunch of terms like this. A sub m alpha to the nth over k. So this is going to be like the impulse response. See, will look like by the inverse C transform of this, and you're going to get all of these terms, e to the 2 pi j m n over k times u of n, of course. So that's what I would get for my impulse response. So you notice you get this exponential, alpha to the nth over k. So let's just take an example. So these are all going to be damped exponentials. If I were to plot, say, the magnitude of h, it would all go, see, and these exponentials, they all are of the form alpha to the 1 over k to the nth. So they're going to decay like this. This is n, and this is like alpha. Let me write it like this, all to the nth power, see? So let's take an example so you can see. Just a simple numerical. Suppose alpha were 0.99. And let's suppose k equals 4. Well, then what is alpha to the 1/4? It turns out that's like 0.9975. So alpha to the n over 4 is like 0.9975 to the nth power, see? So if that were the example, all of these exponentials are the same, and they all decay like this. Well, guess what? Guess what's going on? What's happening is that I started with 0.99. Now, what happens when you take the kth root of a number? you make it closer to 1. See, if you have a number that's less than 1, you take its kth root, it makes it closer to 1, which you can actually see that by taking logs and working with logs of that. So what we've done when we've done this comb filter is we've taken, and what is the impulse response of the prototype? That's 1 over 1 minus AZ inverse. Well, that's just equals to A to the n times U of n, right? So this also takes time to decay, but it decays with A as opposed to the 1 over the 4th, in this case, A to the 1 over 4th power. So this will convert. So H of Z converges generally, for this case, faster than H sub K of Z. And if you think about it, if you let A, where is it? Yeah, if you let A approach 1, this will become a sharper and sharper notch as A goes to 1. And these become much sharper, okay? But guess what? The transient or resettling time of this filter, so if you had an input comprising of harmonic sine waves at all these frequencies, yeah, this output would go to 0, but it would take even longer than it took for our single notch to converge. Why? Because A to the 1 over K is closer to 1 than A is, see? So when I drew this little plot, even though it wasn't clear, sketch, but when I drew it with a purpose. Here I draw A over here. When I draw the poles of this, A to the 1 over, in this case, K is equal to 8, A to the 1, I actually make them closer to the circle, closer to the unit circle. I did that for a reason. Because the 1 over, in this case, 1 over 8th root of a number less than 1 is going to be closer to 1. So in any case, I'll make sure that's scanned in. Please take a look at that. Oh, I see what I did. Yeah, please take a look at that, because that is, I'm getting confused. What am I doing? Poles, hang on. What did I do? There are more. Oh, okay. Yeah. Anyway, yeah, please, I'll make sure that's scanned in so you can take a close look at that. You know, like for the midterm, I probably wouldn't have anything this complicated, but it'll help you for the project. So please review that example. It's can be very helpful. Okay, bear with me here. Okay, hang on. We're almost ready for a break anyway, but let me rearrange something here. Let me put that here. Let me make sure. Okay. Okay. The next up is lattice filters. We're not going to cover those, so forget about lattice filters. So that kind of covers our filters examples. I got a couple more minutes before we take a break. There is one other thing I would like to comment on before I go to actually even a more interesting filter example. We can talk about it after the break. One other thing I'd like to mention is that I showed you the pole zero plots, the Z transforms, and then I actually computed I sketched the magnitude frequency response. There is a way to do that kind of graphically. I don't spend much time with this, but just FYI, there is a way to do this graphically. And the one case was, my example was H of Z equals to Z over Z minus D, where Z over Z minus D, where D is equal to A e to the j omega naught. Okay? So let's say you wanted to estimate, or not estimate, let's say you wanted to compute the magnitude frequency response of this equals what? There is a graphical way to do that, and the way you could do it graphically is take your pole, put the x right there. And in this case, you have 1, 0, it's equals 0. So draw your 0. Now, now move around the unit circle, okay? And at each point where you move, here's your position, e to the j omega. What is magnitude of h e to the j omega? Well, it turns out that's equal to the magnitude of this chord, or distance, from, this is in the denominator, from your point on the unit circle to the pole. Okay, that's what I'm calling L. Similarly, the distance from e to the j omega to your 0, which happens to be at z equals 0, is this chord n. So it turns out the magnitude of h of e to the j omega can be thought of as n over L. Now, for this particular example, n, no matter where omega you are, the distance from the origin to any point in the unit circle is 1 by definition. So that's 1 over L. So basically, all you really have to do is graphically just figure out what this chord is as you go around the unit circle. And what you can see is that as you approach omega naught, in other words, your e to the j omega, as omega approaches omega naught, this chord is just from here to there. That's its shortest point. Vice versa, as you go around the unit circle so that you're on the other side of it, then that chord is the maximum point. So what you would see, if you do it like that, you might get a plot something like this for the magnitude of h of e to the j. You get a maximum here, omega equal omega, and a minimum over there. For this particular case, there is no 0 on the unit circle, so the magnitude frequency response will never go to 0. It'll just kind of do this variation. So anyway, that is the story, and I even discuss a little bit the, and I give you another example, and I also discuss the phase response. So, you might want to take a look at this, kind of interesting. Okay, now I have another example. I will talk about this after the break, but this is a very interesting example where we try to approximate a non-causal filter with a causal filter. So I will see you all in 15 minutes, and all of you handed, oh, there's only 3 of you. Well, anyway, I know. I bet you you'll see some at the very end of the class. Could be wrong. Okay, I'll see you in a few.
midterm?
Yeah.
Uh-oh. Are you ready?
No, not yet. How about you?
Huh?
How about you?
Well, I don't know. I don't know what to expect from a midterm.
There is closed book and closed note.
going to come back to this example because I've got to cover. I want this is a specific example. I will come back to this. But first, I want to finish as much as I will go. Okay, let's see. Bear with me here. Okay, uncover this. Notes I had. Yes. Okay. Yeah, it's probably more important to finish. Okay, so the next example was example 8, equalization filters. So what I'm going to do is, for right now, I'm going to skip over this example, and I'll go to, I want to talk about some more, well, important properties of digital filters. If I have time, I'll come back to this. This is just another example of a digital filter. I used to, in the past, when we've had projects related to this. I'll try to come back to this, or maybe later, but I want to finish the material for the midterm. So, if you look at this example, I call it example 8. It's like 4 or 5 pages, actually. It's not that long. This is the example. So it's like 5, 6 pages. We'll skip over that. I'll try to come back to that in just a moment. And if you're looking at your notes, there is another set of notes, and I will jump to that for right now. And let's see. All right. Yeah, this is, I definitely want to cover this before the midterm. So, actually, by the time I was doing all this talking, I could have finished that. Well, anyway. You never know. Okay. Jumping ahead then and skipping that example. Now, while we are looking at digital filters, and before moving on to sampling, which we will do after the midterm, let's take a little closer look at some more advanced properties of filters relating, because we've talked a lot about magnitude. I haven't talked much about phase and the role it takes in doing filtering. So I do want to talk about phase. That's why this is a little bit more important, because this is more general properties. So I do want to talk about phase of digital filters and what that does to signals and distortion. But before I do that, I just want to make first of all, some very general comments about systems and the phase response and so on. Okay, let's take a look at a system with an integer delay. It's a pretty simple system, and its impulse response is simply that. I call it ideal because it is an ideal example. Delta of n minus nd. Okay? So y of n is equal, therefore, to x of n minus nd. Well, it's a pretty simple example. What is the frequency response? This is the frequency response, and it looks like e to the minus j omega n naught. What is the phase of that frequency response? The phase is minus omega n sub d. Or what am I calling it? I'm sorry, that's nd, that should be nd. Minus omega nd, okay? So that is the phase response of this filter. You notice one thing, it's linear as a function of frequency. It is a linear, this is an example of a linear phase filter. You'll hear that term used a lot in digital processing. Linear phase filter, okay? By that, I mean that the frequency, the phase of the filter as a function is a linear function of the frequency. in this case with a slope of minus n sub d. The filter group delay, I call that tau sub id of omega, is the negative derivative of phi sub id of omega. Okay, so in other words, tau sub id is equal to minus the derivative. Can you see that? Yeah, that comes out. I just can't see it too well on my monitor. Tau sub id of omega is defined to be, I should put a definition, to be minus the derivative of the phase response of a filter with respect to the frequency omega. Now, in the simple example, that turns out to be n sub d. Okay, that turns out to be this delay. So we've come up with a definition of what I'm calling a group delay. I'll explain why it's a group delay in a few moments, and I'll kind of give you a background on where this definition came from. But that definition, minus d phi of omega d omega, it turns out that for the simple example, it's pretty much what you would hope it would be. Namely, it's the actual delay that we introduced in this simple filter example. Tau sub id is the amount of delay, and it's not in terms of seconds, because we're not dealing with seconds. It's in terms of samples. Is the amount of delay in terms of samples, or number of samples, that a narrowband signal at frequency omega incurs as it goes through the filter. A lot of words there. In the case of h sub id of n equals delta of n minus nd, all signal frequency components are delayed by the same amount, tau sub id of omega equals n sub d. So I've used a bunch of words. They're very nice words. Now let's kind of go back and see what all of this means. Okay, so why is it that minus d phi d omega is the what I'm calling the group delay? Why is that minus d phi d omega? Why is that quantity the amount of delay that a narrowband signal at some frequency omega incurs as it goes through a filter? Okay, why is that the case? So to kind of motivate that, to give you more insight to why that is the case, let me consider a general filter, h of e to the j omega. Let's do that. Okay, it's a very simple example, or a very general example. And let's take a narrowband signal. So x of e to the this is x of e to the j omega. Okay, so let's suppose that we had x of n whose DTFT or magnitude DTFT was very, very narrow band, kind of like a delta function centered at omega naught, some frequency omega naught. So this is going to be approximately a sine wave. Or what did I call? Yeah, no, forget it. That is a narrowband input signal centered at omega naught. Okay? That's what the frequency response would look like by definition. Very narrow, bing, 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 centered at omega naught. So what's going to happen is we're going to filter that. Okay? So we're going to look at y of e to the j omega is equal to h of e to the j omega times x of e to the j omega. All right? So what I've sketched on there is, in this plot, I've sketched two things. One, the magnitude of x, okay, which is this narrowband component. And then I've also sketched the magnitude of h. What is it exactly? This is just general. Something. It's some, and I will assume it has a shape that's broader. This is almost infinitesimally narrow, the input, because we want it to be close to a sine wave. But I will assume that the magnitude of the frequency response of this filter is much broader. So it looks something like this, okay? Just some arbitrary sketch. So we can always write h of e to the j omega, Okay, so I will write h of e to the j omega. I will write that as the magnitude of h times its phase, e to the j times phi of omega. Okay, I will write it like this. Now consider a narrow band, for now we'll assume it's complex, signal input centered at omega naught. So that's the plot. And this again is kind of a sketch of what the magnitude of h should be. And we know that the magnitude of y is equal to the magnitude of h times the magnitude of x. Okay? So basically you would take this and multiply it by this. Now you can see that the narrower the signal component is, it's not going to multiply. I mean, all these numbers will just be multiplied by 0. So when you take the product of this times this and let this become very, very narrow, pretty soon all you're going to get is just the magnitude of h at omega equal omega naught. So let's take a look at that. In the vicinity of omega equal omega naught, where the magnitude of x is non-zero, again, we're assuming magnitude of x is 0 everywhere except right in a narrow region at omega naught. Okay? So, in the vicinity of omega equal omega naught, approximate the magnitude of h of e to the j omega. So we're going to we're going to approximate h of e to the j omega magnitude by just the constant value h of e to the j omega naught. Now you say, well, that's not a good approximation. I mean, no, that's true, but in general that's not a good approximation, obviously, unless h of e to the j omega were all passes. But for this example, all I'm saying is that right in this region where x is non-zero, then pretty much h over that very narrow region, I'm just saying it's constant. That's all I'm saying. I'm saying this signal, its frequency response is so narrow that the magnitude of h doesn't change much over that tiny little region. Buy that? Seems reasonable. And if you don't buy it, I'll just make x even narrower. Okay? So all I'm arguing here is the magnitude of x doesn't change in frequency, doesn't change much over this very narrow region. So within that narrow region, I will just approximate within omega, let's see, how do I say this? Within magnitude of x, let me do it like this, is not 0. Okay, so in the region where x of e to the j omega is non-zero, since it's very narrow band, I'll make that approximation. Okay, so that's the magnitude of h. What are we going to do about the phase? Well, let's be a little bit more exact on the phase. What I'm going to do with the phase is this. I'm going to do a Taylor expansion. I'm going to say that I could say that, well, clearly if the region is super narrow, then phi of omega would also be approximated by phi of omega naught. But I'll make it a little bit more, I'll do a little bit better approximation. I'll use a first order Taylor expansion. I will say that's phi omega naught plus, or you know what, forget that. I'll just call that phi naught. It doesn't even matter that it is phi of omega. It's just a constant plus some omega times some a constant d phi d omega at omega equals omega naught. Okay? So that's a first order Taylor expansion that I'm going to use. Right around this vicinity. So you see that in this case, and this is an approximation, phi is to, and the narrower the region, of course, the better this approximation becomes, because there's a smaller range of omega over which magnitude of x is non-zero. So you see that over this region, phi can be approximated in this very narrow region by a constant plus a linear term here. This is omega times d phi d omega at omega equal omega, some constant. Okay? So this can be approximated by A plus B times omega, see? And that's a pretty good approximation. I mean, it's a better one than for the magnitude, which I'm just setting equal to this constant. Thus, we find that the DTFT of the filter output, Y, is approximated by what? Y is well, here, you can read that. Or I think you can read it okay. Y is equal, without the magnitudes, Y is equal to X times H, and now I will write X times the magnitude of H of e to the j omega naught times e to the j phi naught. So in other words, this is just Y equal X times H, and in the vicinity, where an X is very, very narrow, right, I will write it as X times magnitude of H times e to the j phi naught times e to the minus j omega n naught. Okay? What's n naught? Why did I write it as minus j? Isn't it e to the plus j omega times this constant? Well, I've defined n naught to be the negative of that constant. N naught is minus, I'm calling this term minus n naught, see? This I'm going to call, define as minus n naught. So yeah, you bet I can write it like this, by definition. I've just defined n naught to be minus d phi d omega at omega equal omega naught. And so we see that y of n, so that basically this is the DTFT of the output for a very, very narrow band input, right? This is the let me say it again. This is the DTFT of the filter output, assuming a very, very narrow band input x of n with DTFT, capital X of omega. And for that narrow band case, I've used that approximation. And so what I find is that, if I go back to the time domain, what is this in the time domain? This is H evaluated omega naught. This is constant. This is constant. This depends on frequency, and that depends on frequency. So, what we find is that, let's see. Well, it's written right here, but basically what we find is that y of n, well, I'll try to use, can you read it? I guess you can read it. So y of n in the time domain is approximated for a narrowband input, the magnitude of h of e to the j omega naught, constant, times e to the j phi naught, constant, times the inverse DTFT of x of e to the j omega times e to the minus j omega n naught. Guess what that is? That's x, little x, in the time domain of n minus n naught. So, what you've seen is that for very, very narrow band input centered at some frequency omega naught, the output of that input, the output can be written through any filter, h of e to the j omega, can be written as some constant times the input, the narrowband input, just delayed by n naught samples, where n naught is minus d phi d omega, evaluated omega equal omega naught. Bottom line, a narrowband input, sometimes people call that a packet at frequency omega naught, gets phase amplified or attenuated, phase shifted, and delayed by n naught samples. Frequency packets at different frequencies get delayed by different amounts. So that implies that this minus d phi d omega is the amount of delay in samples which a narrowband packet centered at omega equal omega naught incurs as it goes through the filter. Thus, for this reason, the negative derivative of the phase with respect to omega is called, we call that the group delay. So what the group delay means is I have very narrow band input centered at some frequency omega naught, and I know to the extent that it is very narrow band on the input, I want to know what the filter does to it. And what this is saying, as the input gets narrower and narrower in frequency, its bandwidth, what the filter does to it is it attenuates it, or puts a gain on it, puts a phase shift, e to the j v naught, and then it delays it by n naught samples, where n naught is minus derivative of the phase of the frequency response of the filter, evaluated at the center frequency of the input, omega naught. So that is why that's called, that's why I call the group delay, is because that's delay, which is group or packet incurs as it goes through this filter. Now, this kind of bugs me because where's this example? I had a great example of this. Something happened to my example. Huh, I don't have the example. Anyway, I said here, in the Oppenheim and Schaefer reference, which I referenced as background reading, a reference, there is an excellent example of that, and I used to make a copy of that and show it, but I don't seem to have it anymore. Oh, try to show it next time, I guess. No, I didn't bring it. So anyway, that's what the group delay is. In that example, what happened was that they showed a case where different narrowband frequency components went through this filter, and what they showed was that, see, what people typically do, in fact what you can do in Matlab, you can plot the derivative of the phase respect to omega, and that's what they did, omega, and this will show you, for instance, if you had a narrowband signal at this frequency, say, call that omega 1, and a narrowband signal at omega 2, the input is very narrowband, narrowband input at omega 1 has a much larger delay through the filter, through filter than input at omega 2. Input at omega 2. And they had this really neat example where they had a filter which had a derivative of phase, looks something like this, and then they showed what happens with narrowband signals at 3 or 4 different frequencies that go through this filter. And what's interesting is the signal that went in first actually came out last because it happened to be at a frequency with a very large delay. And then there were other frequency components which came through very quickly, but they were attenuated by the filter itself, so you never even saw them in the output. It's a great example. I tell you what, I'll post it. That's what I'll do, so you can see it. It's just an example, and it is an Oppenheim and Schaefer. I couldn't find the equivalent example in our text. Now, before I finish that up, now suppose that phi of omega, which is equal to the phase, suppose it is linear. Before, we said that the derivative of the phase evaluated at omega naught, we call that the group delay at that packet. But suppose the filter, h of e to the j omega, suppose its phase as a function of frequency was equal to minus omega n naught for all omega, okay? I.e., for this case, h is equal to the magnitude of h times e to the minus j times, say, omega n naught. Suppose that. This is an example of something called a linear phase filter. And linear phase filters are very, very important. A filter with this property is called a linear phase filter. Linear phase is a very, very nice property of filters because it eliminates phase distortions. Now, why is that? So you'll see some example. Check this out. let's suppose we have a low-pass filter, and it looks like this, okay? So it has a frequency at omega naught. Everything below omega naught just passes right through the filter in terms of amplitude. We will assume that the magnitude of the filter response between minus omega naught and omega naught is approximately 1. So magnitude of h of e to the j omega is approximately 1 for the absolute value of omega less than omega naught. Okay? And outside of that, we will assume it's 0. So this is a great low-pass filter that will get rid of any noise that's outside of that frequency range. So let's suppose that's our filter. Now you will see what is really, really neat if that filter has linear phase. Very, very nice, okay? Now let's suppose that the DTFT of the input signal, S of e to the j omega, let's suppose that is equal to 0 for the absolute value of omega greater than omega naught, okay? Let's suppose S of e to the j omega is 0 for omega greater than omega naught. So that's kind of interesting. So what we're assuming is that the DTFT of S is all contained in this filter. Okay? All right, so the DTFT of S is all contained inside what we're going to call later on the pass band of this filter. So S will not be attenuated. The filter won't do anything to S. Okay? So when the input signal is in the frequency, in the DTFT is 0, so is the filter. So the filter in magnitude doesn't do anything to the signal. So in other words, magnitude of H times the magnitude of S is equal to the magnitude of S. Or I'll even give you an approximate on that. Okay? So the filter in magnitude doesn't attenuate, doesn't accentuate the magnitude frequency response of S. Okay? So that's that. Now, let's suppose, furthermore, that H is linear phase. Okay? Then the output is given by, so we're going to look at y of e to the j omega, and what that's going to equal to is equal to h times s, which is going to equal the magnitude of h times s times e to the minus j omega n naught. Right? Where did that all come from? Because I assume that h is equal to magnitude of h times e to the minus j omega n naught. In other words, h is a linear phase filter. What is the magnitude response? It's this. It's that low-pass filter response. But I will assume that its phase response is linear. So what is the deal about linear phase filters? Why are they so nice? Well, we'll see. Okay? So what happens? Y is equal to this, and so what does that imply that y of n is? Y of n, therefore, is, to a good approximation, s of n minus n naught. So what that means is that the only distortion a desired signal incurs, when I say desired signal, I mean whose bandwidth is all contained in that filter, the only distortion is a delay distortion, is a simple delay. That's the only distortion that you have when a signal goes through a linear phase filter, in this case a low-pass filter. And this works because we're assuming the bandwidth, we're assuming that the magnitude DTFT of S is 0 for the magnitude omega. So it fits all nicely within this filter, right? So when you have a case like that, the only distortion a desired signal incurs through a linear phase, low-pass filter, is a simple delay if the filter is linear phase, okay? So you think, well, that is pretty neat. So that's pretty neat, because a delay, you can tolerate a delay. But if you had a nonlinear phase in this filter and S goes into it, it's going to, it's really going to mess it up, introduce a lot of phase distortion. Then you have to equalize it and so on. So then you say, great, got it, understand it. Wait a minute. What? So what's the point? I mean, you have a signal that goes to this filter. The signal's bandpass. The filter's bandpass. You outpasses it without any distortion, except for delay. You know what? I got a better idea. I don't even need the damn filter. I just let the signal go straight out, and then I have the signal exactly. Why did I need the filter? Okay? I mean, it's nice that the filter only delays the signal, but why do I need it in the first place? Here's why. What if, what if there's an undesired signal? What if I have like an interference out here, see? If I had a strong interferer, maybe the interferer is right here, okay? So I had some noise, or maybe there's something over here, or maybe there's some noise or something like that. So what if my signal, my input x, was equal to S plus N, see? And the N could be narrowband interference, and we will assume that the DTFT of N is 0 inside the passband, or very small, and is non-zero outside. Okay? That's when you need the filter. Okay? So in that case, an undesired signal that lies outside the signal frequency band, however, is eliminated by h of e to the j omega. This is a very important property. So again, for this case, here is well, I'm glad I did this because I don't think I will have time. Here is the magnitude of h, and here is the magnitude or magnitude frequency response. Here's the magnitude frequency response of the signal. I don't know, it looks something like this. Maybe it's symmetric, maybe not. So it lies totally within the passband. And here is the magnitude DTFT of the input, x. And it looks like this, plus it's got stuff way out here, okay? So I will say that x of n is equal to S of n plus, let's call it I of n for interference, all right? So what happens when that goes to the filter? So the magnitude of it, x times h. Again, since h is linear phase, we will approximate that as x times the magnitude of h times e to the minus j omega n sub d. Okay? This is equal to s plus I times the magnitude of h e to the minus j omega nd. And remember, we're assuming that h, the magnitude of h, is approximately unity. And we assume that the DTFT of I is non-zero outside of the passband of our filter. So guess what that's going to be, to a good approximation? S times the magnitude of h times e to the minus j omega n sub d. What happened to I? It got wiped out. That's what the filter, that's why it's important to go through the filter if you have noise outside of the bandwidth of the signal. In that case, the filter is able to separate it out, get rid of it, and if it's linear phase, then you have that. That is just, to a good approximation, S of n minus n sub d. See? That's why linear phase filters are very important. Now, you might ask, well, what if the interferer lies inside the bandwidth of the signal? And this doesn't work. This doesn't work. But the moral of the story, if you can design a filter, a bandpass or a low pass to have linear phase, please do so. You will minimize signal distortion to a delay. You can typically live with a delay. You can't live with more nonlinear phase distortion. So that is the deal with that. Okay. One final point. that me? Is that you? Me? You? Me? You? No. And therefore, blah, blah, blah. However is eliminated. This is as an aside, here we note that if the phase of omega it's linear but it has a constant to it, then h of e to the j omega is said to be called have a generalized linear phase. Even if phi is stepwise constant over omega, h is still said to have generalized linear phase. So basically, generalized linear phase would be if the phase function, would be something like this. Bingo. And then maybe it's maybe it jumps, and then but it always has the same slope. Jumps, same slope. That would be generalized linear phase. Generalized linear phase. It turns out that filters with the generalized linear phase, but filters with generalized linear phase also have the important property of constant group delay filters over frequency omega, and thus have all the important properties of linear phase filters. And I had an example here. Let's just suppose that suppose phi of omega was equal to minus omega n naught plus, I don't know, some constant b naught. Okay? Then and let's say h looked like this, where a is just the magnitude of h. Then h has generalized linear phase because phi is equal to minus omega n naught plus phi naught. Okay. Anyway, but filters with generalized linear phase also have the important property of constant group delay over frequency omega, and thus have all the important properties of linear phase filters. Okay, so in any case, the takeaway here is linear phase is very important in terms of minimizing distortion to just simple delays. Now, the final little comment I want to make is how do we design linear phase or generalized linear phase filters? And you can do that very simply, as we will see later on in the class, with finite impulse response, FIR filters. And as long as the FIR filters, the finite impulse response is symmetric, the coefficients are symmetric, so we can write h of n equals, so if you design a linear phase filter, and it is an FIR filter, h of n, so it has finite number of finite coefficients, as long as you have symmetry in the coefficients, then the filter will be linear phase. Later on in the course, we will also see how to design symmetric FIR filters that have this linear phase property. So people like these, as we'll see later, FIR filters because they can be designed to have linear phase, therefore they minimize phase distortion of the signal itself. And there are various types of FIR filters with generalized linear phase. We'll come back to this later on. So that I definitely want to cover that. I definitely wanted to cover that. At least to let you know what linear phase is and why it's important. I got a few more minutes. I'll say a word about this example that I didn't get a chance to cover. This is a project we had in the past. This was called digital equalization. I mentioned very quickly phase equalization. This is really something dealing with phase and amplitude equalization. And the idea here is that we have a signal. I'll try to touch on the highlights of this example. We have some signal, S of n, and it goes through some filter, H of z. Linear phase? Not necessarily. Just some general filter, H of z. You get an output, Y of n. Can you tell what S of n is by looking at the output? Not really. Well, it depends on the filter. If H of z is 1, no problem. If H of z is e to the minus j omega n naught, no problem. I mean, it's just a delay. But in generally, no, you can't tell. This filter has distorted your signal. This filter could be a multipath channel, could be anything. So that's where the role of equalization filters come into play. An equalization filter is what I would call an inverse filter to this h of z, such that the output, s hat of n, is the restored signal. S hat of n is approximately to a good approximation. If the equalization filter is good, S hat of n is to a good approximation what the input signal is. Or it could be a delayed version, or S of n minus d. That's okay too in most applications. Delays are fine. But that's the idea of what an equalization filter is. We assume in this example, I'm going to assume the distortion filter is causal, dog whistle, provided all the poles and zeros of h of z lie inside the unit circle, then the equalization filter is stable and causal and is simply the reciprocal of h, okay? Said a lot of things there. I said something about provided all the poles and zeros of h. Now, remember before I said, well, if you have zeros in your region of convergence, it doesn't matter. That's still true. It doesn't matter. But when you're doing equalization, you start to pay more close attention to the zeros of this distortion filter. Now, it turns out you have all the knowledge you need right now to understand the statement I just made. So let me, I have a few minutes. Let me at least explain what I just said. Provided all the poles and zeros of the distortion filter lie inside the unit circle, all of them. And by the way, such filters are called, for reasons that are not obvious right now, minimum phase filters. In any case, provided all the poles and zeros of h, then the equalization filter is stable and causal. Don't you all agree, you three people, that it's good, and those listening to my voice out in TV land, don't you agree that if we're going to build a filter to equalize this signal, it'd be nice if it were causal and it's stable? Agree with me on that? Well, if the poles and the zeros of h lie inside the unit circle, then you can build a stable causal equalization filter. And what is that filter in the z domain? It's very simple. It's just what you would expect it to be, 1 over h of z. So you say, well, that makes sense. If this is 1 over h and that's h, you combine them together, you get 1. So, wow, that's well, what is this thing about the poles and zeros? Why do I care? I just take 1 over h. Well, you care because you want to make sure this must be stable or you can't build it, and causal. All right, so you just kind of see where these zeros come into play in a second. I took an example. H equals 1 minus alpha z inverse. Okay, 1, 0 at z equal alpha. I guess there's a pole at z equals 0. We're not going to care about that. And we will assume alpha is less than 1. So that means there's a 0 at z equals alpha. In this case, the 0 is inside the unit circle. What is the region of convergence? Well, it's everything magnitude of z greater than 0, basically, right? Because it's just 1, 0. What is h of n? It's just a delta function minus alpha delta of n minus 1. So, what is e of z? Well, I'm going to make e of z 1 over 1 minus alpha z inverse. So now my question is, with the magnitude of alpha less than 1, okay? So e of z is equal to 1 over 1 minus alpha z inverse, which in this example is 1 over h. And what is the region of convergence? The region of, since everything is causal, the ROC is magnitude of z greater than alpha, see? Or greater than the magnitude of alpha. So, what about alpha? Is the filter stable? Is the unit circle in the region of convergence? Well, remember, we just said that the magnitude of alpha is less than 1. And it is external to that circle, so that implies, yes, sir, it is stable and causal. Wow, not bad. So that's pretty simple. So there's your distortion filter, done. Now, of course, an issue is, do you know what alpha is? You have to know what alpha for this to work, but you can estimate it. But that's much beyond this. So there's a simple case. Alpha is less than 1, everything's stable. Okay? And then you can look at also as, you can look at that in the time domain, and you will convince yourself, yep, output is S of n for that case. Now what happens if the zeros of H lie outside the unit circle? So let's go back to that example. H equals 1 minus alpha z inverse, but in this case, magnitude of alpha is greater than 1. Okay? So it still has 1, 0. It really has a pole that's equal to 0. It still has 1, 0, but now the 0 lies somewhere out here. Okay? That's c equal 1. All right? So now the 0, that's supposed to be a 0, lies outside the unit circle. Okay, big deal. Who cares? Well, now we care. And I'll tell you why we care. Because let's use our trick again. H is equal to 1 over 1 minus alpha, z inverse c. And I will demand, I want to make this something you can implement. So I will say H is causal. Okay? Then you say it is causal. Fine. Then the ROC is magnitude of z greater than magnitude of alpha. And it includes the unit circle. It doesn't include the unit circle. That's greater than 1. So what this is saying is it is unstable. But it is causal. And causal. So that doesn't help you very much. What if you said, okay, forget that. Suppose H is, now assume, oh boy, H is non-causal. Crazy? Maybe. Suppose it's non-causal. Well, in that case, then it's interior to a circle. Then ROC is the magnitude of z less than the magnitude of alpha. What about that? By golly, magnitude of alpha is greater than 1. Unit circle's there. So this is stable. Look at that. You heard that expression. You can't have your cake and eat it too. Well, this is a good case. You want it causal? It's not going to be stable. You want it stable? It's going to be non-causal. So that is why these 0 locations, which weren't important before, now they've become important. Now the zeros of this filter, when you're talking about equalization, become very important. So what I did in this example, so since I don't have very few minutes, I'll kind of speed you ahead to show you what I did. What I said was, well, look, stable's important. I'm going to give up causality for the time being. I'll make this filter non-causal, but it will be stable. Let's see what I get. So if you look, and I worked all these notes out, plus all the Matlab code is actually in here that I used to generate plots. Like, see this plot? There's the Matlab code. So question I asked myself is, suppose that E is not constrained to be causal, but we want it to be stable. So basically I'm asking, what is the inverse C transform of 1 over 1 minus alpha Z inverse when we know that H is non-causal? So in other words, when the ROC of H is inside inside that circle. Well, we've already worked that out, and we know what the answer is. We know that the inverse transform of the H of Z, or I'm sorry, this is not H, this is E. Sorry. Now assume E is non-causal. Yeah, sorry. That's E, not H. Okay. So E. So what does E of n look like if we constrain this equalization filter to be non-causal but stable? Well, I worked it all out, and this is the result for the impulse response. It's this minus alpha to the n thing times u of minus n minus 1. And yes, that is stable, even though alpha is greater than 1, but because this is only evaluated when n is less than 0. So this is stable. Stable if magnitude of alpha is greater than 1, so that's no problem. And here's a plot of it. Looks, few minutes. Looks like this. This is the plot. So it is large here, and then it gets very small. But the point is, this is for negative n. So then I said, so that's non-causal, but stable. That's E of n. So then I said, well, I got an idea. Let me worry about, so at least I got something stable. It decays to 0. Now let me worry about the non-causality. What I'm going to do is I'm going to create a new filter, E hat of n. Oh, well, I'm sorry. I'll just do this. Okay, the first thing I'm going to do is I'm going to truncate this at some point to 0. How many?
5.
Okay, all right. So I will set that to 0. And with that 0, this will be what I call E hat of n, okay? And then, so now I have a finite impulse response filter. That's an approximation of this, where I just set that to 0. But it's still non-causal, so you know what I'm going to do? I'm going to delay this whole thing and move it over here. And that is this approximation. So it has the same shape, pretty much, except I did truncate it to 0, in this case with 40 samples. But now it's causal. So I just took this, truncated, and moved it over. Now everything is causal, finite, and it's a finite impulse response filter. So we can build this. We couldn't build the unstable one that's causal, but we can build this, and it is causal, and it's approximation to the non-stable solution. And when I did that, what I found was that I had this, so when I took E of n, I should say E hat of n, my approximation, I call it E double hat, and I convolve it with h. What I want to see is delta function. Well, I don't see the delta function, but I see something kind of like a delayed version of the delta function, which almost looks like the delta function. This is delta of n minus 40. So what it's done is it has restored the signal with up to this one delay, not bad, and then there's a little bitty boof right here, okay? So the moral is that even if the zeros of h lie outside the unit circle, we can still approximately restore S to within a delay using a causal FIR filter. So that is my example. And if you delay it even more and do a better job of truncating it, as I used with these examples where the input was this function, this step function, then you can even do a better job with more delays. So it depends how many delays you can tolerate. But typically a delay of the signal is much better after you've done this equalizer than phase distortion. So that is that. And that is all that I wanted to cover. I just barely made it. So what I'm going to do is this. I'm going to post a set of just 2 pages of basically what we've already covered, okay? Kind of what you're responsible for in this midterm. To review, again, the midterm, it's next Wednesday. I think it will be here. It starts at 6:30. It's 2 hours long. That's it. No other lecture, no nothing like that. Closed books, notes, and counts for 30% of the grade. And you should bring your calculators. You may need them. I don't know yet. I haven't made up the exam. So we're going to cover on the exam sequences and systems, the DTFT, and digital filters, some of these examples we went through, including the linear phase stuff. That's what you have to know. I will post that on the web. I will post the solutions by no later than first thing Saturday, homework 2, and a spatial homework set. And I will post these notes so you can make sure you know what's on. Then I will do one more thing, just because I like you. I won't do this for the rest of the class. No, I'm kidding. After I've made up the midterm, probably no later than Monday, then I will send out another email to the class telling you more specifically what sort of areas are on it, so you don't have to worry about studying for extra things. The problem with this is probably most of these areas will be on it. But anyway, if I can narrow down the scope of the midterm, I will do that, and I'll let you know. So that is it. Okay, great. You 3 guys, very good. Got your homeworks in. I'll see you next Wednesday for the midterm. So I will post where it will be, but I'm pretty sure it'll be here, 'cause we have plenty of desks, so. Okey doke, thanks.
This has been EE483 on Wednesday, June 18th, 2014.